Today we're going to talk about lesson 4-4, matrices for size changes. So we've dealt a lot with matrices, okay? We've added them, we've subtracted them, we've multiplied them by a scalar, and now we're going to use matrices. We multiplied matrices. So we're going to use matrices now to multiply to other matrices to get size changes, reflections, etc., etc. The big idea today is we're going to take 2 by 2 matrices and represent them as geometric transformations. Okay? So, in the next few lessons, we're going to see how matrices can represent a variety of geometric transformations. Recall from geometry that a transformation is a one-to-one correspondence between the points of a pre-image and points of an image. Okay? So you start with a set of points, you do a reflection, a transformation on something, then you get an image. Okay? It says consider the transformation S of k that maps x comma y onto k times x comma k times y. If k equals 5, that means this is 5, that means these are 5. The transformation images of a few points under S of 5 are written as follows. So, all this means is you're taking each thing times 5. Okay? 5 times 2 is 10. 5 times a negative 3 is a negative 15. Same thing down here. S of 5 to that point. 5 times negative 3, negative 15. 5 times 0, 0. So on and so forth. So in general, S of 5 times the coordinate point x comma y equals 5 times x comma 5 times y. The definition of a size change. For any k where k cannot be equal to 0, the transformation maps x comma y onto kx comma ky. Is called a size change with center 0, 0 and magnitude k. Okay, my center is the origin, and is denoted as S of k. I like to use this way to write the definition, but you will see this mapping way. All they did was put colons in here and then use this arrow to say maps to. Okay? It is read under the size change of magnitude k and centered 0, 0. The image of S, k is k times x, k times y. Or the size change of magnitude k and center 0, 0 maps to x, y onto k times x, k times y. Okay? So let's look at example 1. What is the magnitude of the size change that maps the pre-image try onto its image T prime, R prime, I prime as shown at the right? Write the size change using mapping notation. So that's this bottom one right here. That's this mapping notation. So in essence, what we're trying to do is figure out what K actually is. Okay? So we're trying to figure out K. So that's our great unknown. And I'm just going to rewrite this because this is going to be our answer once we find K. So if you look here, a negative 1 goes to or maps to a negative 4. R1 maps to 4. And I1 maps to 4. If you look at your y values, 2 maps to 8. And 4 maps to 16. And a negative 3 maps to a negative 12. So if you look at these, basically all you're asking is 2 times what number gives you 8? 2 times what number gives me 8? Because that's what happens in a size change. Well, if you divide by 2, x equals 4. Does that work for all of them? Yeah. Negative 1 times 4 is a negative 4. 1 times 4 is 4, etc., etc. So my k is 4. Put a 4 there. 4x, 4y. Okay? Moving along. Using matrices to perform size changes. As the activity illustrates, size change images can be found by multiplying matrices. When the matrix for the point x comma y is multiplied on the left by k, 0, 0k, the matrix for the point k times x, comma k times y results. Okay? So I need you to know this. Size change theorem. Okay? You need to know this matrix. And this, as they said, always has to be on the left. Okay? Why? Because this is a 2 by 2. And when you multiply it to some matrix, it doesn't matter, or a coordinate matrix, this is always going to be a 2 by something. Now, if you have 5 points, okay, that means you have 5 columns. So if I do a 2 by 2 times a 2 by 5, I'm going to get out a 2 by 5. But if I were to flip these around and go a 2 by 5 times a 2 by 2, it doesn't work because these rows and columns don't match up. So it's very important to put your size change matrix always on the left. Okay? When k equals 1, the identity matrix 1, 0, 0, 1 maps each point x, y of a figure onto itself. So this matrix gives you the original matrix. If I were to take 2, 3, 4, 5 and multiply it to 1, 0, 0, 1, I would get out 2, 3, 4, 5. Okay? You're getting out the same thing when you multiply by the identity matrix. This size change of magnitude 1 is called the identity transformation. Example 2 says, using the figure from example 1, perform the appropriate matrix multiplication to find the vertices of the image T prime, R prime, 1 I prime from the vertices of the pre-image. Try. So, the solution to this, okay, if you remember, we're doing S of 4, it says. Okay? We're doing S of 4. So if you remember, 4s go down the diagonal, 4 and 4, zeros everywhere else. 4 and 4, zeros everywhere else. Okay? Now I got to get my other points from my first triangle, so I got to go back here. And it's negative 2, comma 2. So it's negative 2, comma 2. 1, 4, and 1, negative 3. 1, 4, and 1, negative 3. Okay? Now, I'm going to show you a little shortcut when doing these. Okay? You can put this on your calculator. Take a 2 by 2 times a 2 by 3. But I want to show you what's going to happen is if you take row 1 times this, you get this number times this number times this number, and always this second number here is going to get plus 0, okay, because 0 times anything is 0. So essentially what happens is you are always taking 4 times a negative 2, 4 times 1, and 4 times 1. Now this is just only with these size changes, okay? So don't confuse it with any other matrix multiplying to another matrix. Only for size changes. So what I'm saying is you should take, sorry, did I put the wrong point here? Yeah, t is -1, sorry. So let's go back here. I got -2 down. I think I wrote it a little weird, so this should be a -1. Pardon me. So 4 times a -1 is a -4. 4 times 1 is 4. 4 times this one is 4. Now, what happens on the bottom? Well, 0 times this number is 0. So always those are going to be 0 up on top. So it's going to be 0 plus whatever this times this is. Well, 4 times 2 is 8. 4 times 4 is 16. 4 times a -3 is a -12. Now, like I said, that's only going to work for your size changes. If you were to do this times this on your calculator, you're going to exactly get this matrix right here. So here's my pre-image. This is my new image. So my new images have vertices a -4, comma 8. Because remember, it goes x, y, x, y, x, y. R prime is 4, comma 16. And I is 4, comma -12. Size changes in multiplication of distance. Recall that the Pythagorean theorem can be applied to calculate distance between 2 points. Remember, Pythagorean theorem can be ran on right triangles. Okay? Here this forms a right triangle. So we would be able to find the distance of all these sides. Suppose you wish to find the distance AB when A equals x1, comma y1, and B equals x2, comma y2. If you don't remember the general formula, and if you remember, we said c squared equals a squared plus b squared. Please don't remember that. That comes in very handy a long, long ways down the road. So, all this is saying is c squared equals a squared plus b squared. All you did was take the x's, subtracted them, squared them, take the y's, subtracted them, squared them, and take the square root of each side, and then you have the Pythagorean distance formula. So you take your x values, x2 minus x1, get your answer, square it. Take your y2 minus your y1, square it, and then set that equal to c squared, which is this side right here, and you're going to end up finding your distance. Thank you very much. That's all I have for you today. Please remember this. You're going to need it in trig and everything else. We'll talk to you later.